So, this is the first introduction on the summer course on VLSI design and CAD. We have named the course as a first course on VLSI design and CAD because we assume that none of you have any background on specifically VLSI design and CAD, though I believe many of you have already done a couple of courses on different aspects of circuit design and a few courses on programming and algorithms kind of things, right. So, with that we will start this course, and we will start by having a brief overview of the background against which VLSI and chip design industry is growing and it is taking place today. So, if we look at the history, and believe me that we have been we means I mean most of you were not born at that time. So, when I am saying we, it refers to me and my colleagues particularly. We have been very privileged to see a very spectacular amount of change that has taken place in the computing industry in the last 2 or 3 decades. So, if you look at the 1980s to 1990s, what happened was that computation, which was the main bottleneck, became free. Now, what do we mean by that? I joined this institute as a BTech student in 1986. Only a couple of years before that, the best computer that we had in the institute was a punch card machine. So, people would queue up with a stack of cards which actually contains the program encoded in the punch cards at 6 o'clock in the morning and wait for their slot for running the program. So, they would queue up outside the computer center, the cards would be taken and then it would run on the computer. Another set of cards containing the results would be given back to the student. And then if you realize that in the for loop, instead of do you had written D0, well then at 6 o'clock next morning you are back there in the queue. Okay, so that was how it used to be. Then when we were in our first and second years, I recollect we used to have a Hewlett Packard 1000 series computer, HP 1000. It did not have a microprocessor. It used to have the CPU of the processor or the central processing unit was a 8-layer PCB and the wiring was in gold, and that 8-layer PCB was the CPU. Today the CPU is this small. In fact, the actual silicon is much smaller, you can't even see it with the naked eye. So, that kind of CPUs used to be there, and it won't boot on its own. It is not like you switch on the power and it boots. You have to set the values of all the registers, load the program counter and then it starts, right. So, there used to be a chart which told you how to boot the system, right, and our dadas used to take the privilege of not sharing it with the juniors. So, only senior students had the privilege of booting the computer, right. And then we had the HP 9000 series computer, and believe me that you can't compute more than factorial 13 using a recursive function. Why? Because the heap and stack would collide. So, anything above factorial 13 levels of recursion, you have a heap stack collision, right. And the language that we used to use is Fortran and Pascal. No C was there at that time. At least we did not have it. So, from that what you have in the 90s was that you have enormous amount of power packed on your desktop. Today it is unbelievable amount of power on your desktop. So, what has happened is, and the cost has gone down actually. So, computation power, raw computation power has become free. It is easily available, low cost. We do not worry about that anymore. Okay. What happened in the 90s to 2000? Storage became free. Okay. I will show you some pictures showing how this happened. We used to have a 260 GB hard disk. 260 GB was it? No, 260 MB hard disk. It was so big that we used to carry it on a trolley. So it was a box larger than the largest suitcase which your airlines will allow. Okay, and you can just drag it along the trolley, and it was really heavy, right? From that to almost 20 times that space on a small pen drive today, right? That's the change that has taken place. So storage has become free in the last decade. Now in this decade, what's happening? Communication is becoming free. In the last decade, the main issue was bandwidth. Bandwidth was very expensive, but in this decade, bandwidth is slowly becoming free. Now what we need to understand is that how did all this thing happen, and what is the next things that are going to happen from here on. Here are some nice pictures. This is a 1954 prediction of a home computer at 2004. So in 1954, this gentleman predicted that in the year 2004 a home computer is going to look like that, right? And this is actually how it looks. This is the iMac, okay, the Apple iMac, in which you must have seen this machine. Have you? So you don't have that box, the actual computer anymore. It's all fitted inside behind this screen. Okay, so this is all that you have, and you have the keyboard and the mouse. Okay. This is what I mean by storage becoming free. The picture in the middle is quite interesting. It's a 5 MB hard disk being loaded into a aircraft. Okay, that's a 5 megabyte hard disk. On the left hand side, this is a magnetic tape drive. I believe many of you may not have seen this because they probably became obsolete before you were born. But we saw a lot of these. Anything that needed to be backed up used to be backed up on these tapes, huge magnetic tapes. And from there, this is a 4 GB pen drive. This slide was also made a couple of years ago. So now you can replace that 4 by something like 32 GB, right? You recognize that telephone? You have seen it only in films, right? We did use it for some part of time, but again in our childhood also it became obsolete. So that's the grand old telephone. And from that, here on the other side we have a Windows Mobile, which has everything in it, the iPhone, the Apple iPhone. And this picture, this graph shows the growth of the number of cell phone subscribers in this. So one interesting thing that we have to understand is that the new generation computation is not about building larger and larger computers anymore. It is about making efficient, portable, computable devices. Okay, the shift has been from we have a lot of power on our desktops. We don't seem to be needing any more of that, but we need a lot more in our handheld devices. So that's where a lot of focus is going into. A lot of the leading chip design companies are trying for their share of the pie in the mobile portable devices segment, right? That's going to grow in enormous amounts, and I'll talk some about these things a little more. The other thing that has really grown is interfaces, the human computer interface. So this is the punch cards that I was talking about. The program will completely be encoded in these punch cards, and there were different ways of creating those punch cards. Now can you read the name of the company here on this one? IBM. So you see, IBM used to manufacture these hand punching devices also, right, at some point of time in the future, in the past rather. So this is that the manual punch card machine. And then after that, these paper tape machines were there for some time. The difference was that these are all set of punch cards that used to be loaded into the computer, and this is something which could be fed directly from the machine which was printing out the paper tape. The paper tape could run directly into the computer, and the result would come out from another paper tape and go directly to the printer. So that was thought of to be a highly automated human computer interface, right. From there we had this, the first time when the cathode ray terminals came into existence. So everyone was very excited about that. Believe me, we have seen these paper tape computers. They used to be here in electronics department. They procured a paper tape machine. Previously we used to have only punch card machines, not many years ago. Okay. Now where are we heading to? This is a Bluetooth laser virtual keyboard. So this small thing that you see here, the size of a pen drive, is all that you carry. Okay. So you just put it on the table and it projects a laser keyboard on the table, and you just type on that keyboard, right. That is it. And actually this is only half of the thing. The other half is another small piece like that, which projects a screen on the projects a picture on the wall, and that is your computer. So this is the keyboard and that is the computer. So whatever you type in, you see on that screen. Okay. And that two together, you can just put them in your pocket and travel around with it. Okay. That is about then the next generation interfaces. Now what makes this possible? The core technology behind this is the science of designing and manufacturing electronic circuits, which is an incredibly complex technology, and it's mind boggling that how it actually works, but it has been made feasible through generations of research and practice. And the key thing there is that the design methodology, which you will study in this course, is a very streamlined, well defined design methodology, and it is assisted by excellent CAD tools which again have been developed through generations. And then there is also the streamlined manufacturing of these chips, which is handled by experts. Okay. And if you look at this industry, well, there are three different things here mainly. There are three different components in this industry. You have on one side the design companies, the ones which design chips. Okay. On the one side you have the CAD companies, CAD or EDA companies. I will tell you what are the full forms of these. And the other side you have the fab companies. Now let me explain what these are. The CAD, computer aided design, and the EDA or electronic design automation, these tools are used to design the chips. Okay. These are software companies, companies who design these chips, who design these tools for designing chips. What are the leading companies here? Well, you have Synopsys, you have Cadence, you have Mentor Graphics, and many others. Okay, they specialize in developing CAD tools, EDA tools, right? And they need computer scientists, they need people who understand design to be able to develop these tools. Then we have the design companies, the ones which actually design the chips. So we have Intel here, you have Texas Instruments, you have National Semiconductors, okay, you have IBM, Sun Microsystems. These are all chip design companies. They design chips, from processors to other types of chips. And then you have the fab companies, the companies which actually take the designs and produce the silicon. So they own the fab machines, the machines which fabricate these chips. Now previously many of the design companies used to own fabs, their own fabs. But increasingly, because the fab is becoming very costly and very sophisticated because of the shrinking geometry of the transistors. Transistors are becoming smaller, 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 smaller. So it's becoming so sophisticated technology. The fab companies are become entities on their own. And there are many leading design companies like Sun Microsystems who don't have any fab of their own. They just do the design and get them fabbed out from professional fabs. Okay. So there are people who are experts in device physics, people who are experts in the semiconductor devices, etc., and the people who know how to handle those machines. They are in the fab business. Okay. The design guys are the ones who think of new architectures, new products, new applications, new chips, and they design those things. Right? The CAD companies work with them to find out what are their tool requirements and develop those tools. Okay. In this course, you will get a lot of this part, how design is done. You will get a little of this part and a very little of this part. Okay. We have research groups on all three of these in various capacities. Okay. The new challenges are that we have to do things with low cost, with low power, and we have to look for applications which change the face of humanity. Computers will not be just computing devices anymore. So that's why you see a lot of new applications coming up in areas like medical instrumentation, in automotive. Most of the automotive is electronically controlled. When you have you will see a huge truck having how many 24 wheels or something like that, and from that you will see a very thin and skinny driver coming out. How is he driving that huge truck? Right? But that's because it has a power steering. What is a power steering? When you turn the steering, it doesn't actually turn the wheels. It just passes on this information to a processor, which in turn uses a motor to turn the wheels. Right? So it's not that you are spending the effort in turning, that work done to turn the wheels is that energy is coming from you. No, there is a processor which is controlling that. And not only that, that processor is also giving you a feedback. So if you are driving fast and then you want to turn at that, you will see that the steering is stiff in your hands, because that one is giving you a realistic feedback about how much effort is required to turn at that high speed. Otherwise, there will be no control. You will not learn how to use the power steering. You may turn it very rapidly in a very high speed, and the consequence will be that the vehicle will topple. Right? Similarly, you must have heard of anti-lock braking systems, ABS. They are very sophisticated processor controlled technologies to decide when you will brake. If you just jam the brakes when you are in a big high speed on a skiddy road, it will not brake, it will just skid. But your intent is to brake, your intent is to stop the vehicle. So just putting the brakes is not the solution. You have to understand what kind of braking, how much of time, maybe set it, release it, what, so that the vehicle actually comes to a stop. Right? So these are sophisticated technologies coming into the automobile. You must have heard of fuel injection. Fuel injection controls the amount of fuel that is going into your engine all the time, and that is also controlled by a processor. Previously, you may recall, you may not recall, because again you were not born at that time. People used to take the vehicles to the garages for tuning. What was that tuning? You turn certain screws to determine how much of fuel is going into your engine. Right? Otherwise, you will find that it's running fine but eating up a lot of oil, and much of that oil is not burning, which is causing environmental pollution also. So you need to determine exactly how much fuel has to go there, and these are all software controlled, processor driven technology. Right? From that to a new technology which TI seems to be coming up with, is to enable a blind man to see. So what are they trying to do? They are trying to put a small device on the optic nerve which will capture the images from the eyes and then create the exact sensations on the optic nerve as would happen in a real eye, and that gives the blind person vision. May not be continuous motion, but at least in snaps. So that's a phenomenal kind of technology, right? Then you have all these new technologies for drug delivery. You implant something in your under your skin and it continuously delivers drugs, something like insulin, for example, for a diabetic patient, controls the amount of insulin that has to go in depending on his needs, right? So this is where the new generation technology is going to, and we must be aware of that because we need to focus on developing solutions for that kind of thing. This is something which you must have seen before. This is Moore's law. Moore's law says that the number of transistors doubles approximately in every 18 months, right? So this gives you the number of transistors that are there in the Intel family of processors since 1970 to around our time, okay. And this Moore's law seems to be holding for so much long time, whereas people had actually written it off when it was proposed, but it still continues to hold, and it is becoming a real challenge now because the transistors have become so small that we are beginning to see quantum effects in the silicon, right. So I mean, people are still skeptical about how long we can hold on to Moore's law, but they had been skeptical since 1970 and it still has been holding, right. So we don't know. This shows that the way the cost is going down, the cost per transistor, okay. So starting from about $1 million in 1965, in the 1960s, late 1960s, to about 10 cents in 2005. Okay, that's the cost per million transistor. Now see that, have you heard of anything else whose cost goes down? Apples, oranges, vegetables, right? This is the only thing whose cost goes down in the world, believe me. Now this is what is the real problem that we are facing. We are packing in a lot of transistors in a very small amount of place. The geometry of the transistors are going smaller and smaller and smaller. We are packing more and more transistors on the same amount of die. The consequence of that is that the amount of power dissipation that takes place in that small amount of area is huge. To give you an estimate, a Pentium can easily consume at a point of time more than 5 amperes of current. Now that's a huge amount of current considering that the chip itself is this small, right? It's dissipating that amount of power. Now this picture taken from Intel gives a prediction on how this is going to look like. And now if you look at the Pentium family of processes, it's already approaching the temperature of a hot plate, okay. And if it grows like this, then we will reach the nuclear reactor and then the rocket nozzle, right. Now what can we do about this? So the paradigm of designing chips has completely turned over. Now power is the key issue. It's key issue for two reasons. If you look at the portable power devices, these ones, if they consume too much of power, then you will have to charge your battery every hour. You don't want to do that, right? You want to have everything on your phone. It should be like an iPod. It should have all the features of, you should have lots of games. You should be able to see movies here. You should be able to make phone calls from anywhere in the world, right? Low signal, high signal, whatever, okay. But you want it to run for hours without charging, right. That is only possible if the devices that are running here do not waste any amount of power, and they are made for low power application, right. This is a big challenge. At the other end of the spectrum, Google is planning, or most probably they have done it already, I am not aware of that, of building a data center under the riverbed. Why? Because the kind of servers that they have to keep, for all your, for example in Gmail, for all your mails, for their search engines, the amount of data, the amount of number of servers that they have to keep. For that, in their data centers, air conditioning is a huge problem. You will spend more money on air conditioning than on maintaining the servers, because of the heat that all these servers will generate, right. That is a very non-trivial problem today. How do we manage so much of high volume computation and do it in low power so that you don't heat up the space? That's why you think of putting your data center under the riverbed, so that the riverbed acts as a cooling, right. So that's where we are looking at. So most probably in not too distant future, we will have most of these things under the seabeds. Right. To give you a glimpse of this picture on the left side is a cyber computer. We used to have a cyber computer here in IIT Kharagpur. These cyber computers were based on a ECL technology. You have heard of MOS. Have you heard of TTL? You have heard of that. Okay, ECL is another logic family like that. Okay, it's a logic family like MOS, like CMOS. So that ECL is a very fast logic, because the switching speed is very high, but the current consumption is extremely high. So that's why if you look at this, you see these pipes here, these pipes are pipes containing supercooled refrigerants. Okay, they run those pipes all above the circuit. So you have the circuit boards, and just above it these cooling pipes will run, right, and that's how they would keep the system cooled. Okay. These are more modern types of coolers, but they are not for ECL technology, so they don't need that amount of cooling. This is a fan. You see, if you open up your PC, you will not be able to see the Pentium, because it is sitting right underneath the fan. Okay, this is a fan. If you plug out this fan, you will see that below it there is a Pentium. So you have the fan right on top of it to dissipate the hot air building up on top of the chip. Okay, this is another type of cooler used in some of the machines. Now, in spite of all this, each of these processors, they spend a significant amount of time in thermal shutdown. So you are not aware of that. When the processor runs, when it reaches the temperature beyond which it cannot work, it simply goes into thermal shutdown. The processor just stops, right, and it cools down and then starts again. You don't see that, because it all happens so fast that you don't see that. But a significant amount of your processor time is spent in thermal shutdown, in spite of all this. And people are looking at new kinds of technologies, and we have a very good research group in the institute which works on that. These are called microfluidics based cooling. So what happens is that in the silicon, just above the silicon, you create some very small molecular level structures for carrying small drops of liquid to the places exactly on the silicon which are getting heated up. Now the whole of the silicon is not getting heated up. It is only some regions where you have more switching activity that's getting heated up. So at this point of time, maybe this part is getting heated up, at that point of time that is getting heated up, and this actually delivers the fluid to exactly the places which are heating up, and then the fluid vaporizes there and takes the latent heat from the silicon. So this is called microfluidics based cooling. This is a very sophisticated and very interesting technology, and there is a group here in IDKGP which works on this technology also. Right, now let us look at the chip design from concept to market. So there are broadly two things that you will study about. One is pre-silicon design and post-silicon. Both of these are very important parts of the chip design process. In the pre-silicon, we typically start with the specification of the design and then develop the design. Here we use different kinds of languages. So for analog design, you can use the schematic editor, and you can use languages like SPICE to describe, or Verilog AMS to describe models of circuits. In digital design, you will use Verilog or VHDL to describe the implementation, and then there will be synthesis tools which will take it down to the gate level design, and then the transistor level design, and then to the tape out. In the post silicon also, this partially overlaps with the design process. Why? Because a lot of bugs and lot of design errors are found after the first silicon is available. So we typically call that a prototype. The prototype can be in silicon or it can be on something like FPGAs, and then this cycle, after it completes, then the final manufacturing takes place. Manufacturing is the process of producing all the chips, right, and then those chips will have to be tested before they are delivered. Now there are two types of testing that we are talking about here. The first silicon is tested for design errors, whether there are errors in the design itself, right. The second, the manufacturing testing, is to make sure that the machine which is manufacturing the chips is producing exactly what has been designed. You get it? So this is more thorough because it tests all possible behaviors and makes sure that the design is correct. This cannot be that thorough because you cannot spend an hour for every chip when you have to tape out 50 million chips, right. So you can't test each one of them for 1 hour, then you are not in the market anymore. So you have to judiciously decide exactly what has to be tested here within the time limit, so that you can make sure that there are no manufacturing defects in the chips that you are shipping out. Let us look at the circuit design considerations. First thing is, we must minimize delay. Chips must meet the necessary timing requirements. Okay. All of these slides will be made available on the website, so you can access them later on. Okay. We want to minimize area. We don't want to have a large implant for the pacemaker. It has to be a small thing. Minimize power. You don't want to have a pacemaker replacement operation every year, right. So ideally, once you implant a pacemaker, it should run for the rest of the life of that person, right. Now here there are two problems. One is, battery technology is not growing at the same pace as the chip design company. So chips are becoming very sophisticated, very fast, very efficient. Battery is more sluggish. It would be ideal if you could have very long lasting batteries developed, technologies developed for that, but that doesn't seem to be happening. So how do these pacemakers run for years? Okay, our watch batteries don't last that long, and this pacemaker, what does it do? It stimulates the pacemaker nerve so that the heart keeps on pumping. How does it run for so many years? It's because it doesn't run all the time. It actually allows the heart to take it up on its own. It only acts when the heart doesn't. So when the heart starts missing beats, then the pacemaker takes up and then starts working. When the heart is all right on its own, it doesn't do anything, right? So these are the fine things that it, by monitoring that thing, it can save a lot of power. This is a very important thing. Verification is taking up more than 70% of the time that you invest in designing a chip and putting it in market. More than 70% of that time is spent in making sure that the chip is correct, right? And if it is a critical thing like a pacemaker, we have to be dead sure that the design is okay. Then verification and reliability are not the same thing. Verification is about making sure that what you have designed is correct. Reliability is about making sure that the actual physical components are reliable, that is, they won't fail. That depends on the fab technology, that depends on how you have designed it so that it won't fail. Okay. So you may have redundancy also. You may have some circuit components which are replicated just to make sure that it is more reliable. Testability is very important. We need to make sure that the design is testable after it is manufactured. So we put in special structures inside the chip which allow us to test, because once the silicon is there, you can't see any part that you like inside the silicon. It becomes like a black box. You can probe certain points, but not all the points. So testability is all about making sure that you have put in right structures inside the chip so that you are able to get more visibility on the inside of the chip to make sure that you are able to test it. Final thing is reducing cost. This is very important, particularly in the medical domain. Otherwise, all the technology will become inaccessible for 90% of the world's population. To give you an example, a typical USG is going to cost here about 500 to 600 rupees. That is beyond the spending power of most people, even just outside the IIT campus, right? So new technologies are coming up where the USG devices will be portable. You can carry it on a suitcase, and you can, today you can take it to a village, do a USG at 100 rupees cost, okay? But even 100 rupees is a lot. So companies like GE and TI, they are trying to bring that cost down to something like 20 rupees, right? That's where we will really be able to penetrate the technology into the masses. Unless we are able to do that, it becomes a very niche thing for only a select set of. Look at how cell phones have penetrated, right? Because today you can buy a cell phone with which you can do all the essential things in 1000 rupees, right? It will go down even further, right? And it's available everywhere. In very remote places also you will see that you are getting access to cell phone, and people use it also. Now that's the kind of penetration that we should have. Okay. Now what is the new kind of device is going to look at? So previously we used to have these as separate chips. Processor was one chip, memory is another chip, and then processor and memory typically communicate with a very fast interface, and then you have a bridge which connects to the peripheral bus, and the peripheral bus has all the peripherals, which means the digital circuit components and the analog circuit components which interface with this bus through digital interfaces. And you have the central power management, the platform power management circuitry, which decides which of these blocks should be on and off at specific points of time. Today this whole thing is going down into 1 or 2 or 3 chips, packing all of this whole thing into 1, 2 or 3 chips. For example, if you look at Intel's MID architecture, MID is the mobile internet devices architecture. They have actually packed these things all into 3 chips. Why? Because they are very small, you can pack them together, and that is the core computing platform for your cell phone or PDA or portable device, right? So that's what is happening. And you see here, other interesting thing is on the same chip we are going to see more and more of both digital and analog, right, which is a major challenge. These are the broad domains of expertise. I left out the fab here, it should be there also here. That is, you can learn analog design, RF design, you can learn digital design, you can learn CAD, and you can also learn about fab technologies or semiconductor technologies. Let us compare the design flows of digital versus analog. You will see more of this in this course. In the digital design, the entry is in the Verilog or VHDL. Okay, so you use a high level language like Verilog or VHDL to enter the design, and then you do a behavioral simulation. You simulate that design as a whole to see whether it is behaving in the way that you expect it to. Then there are automated tools for synthesizing that into the gate level designs, and then you do a place and route. What is the place and route? For each of these blocks that you have synthesized, you have to put them on the chip floor, that is the placement. How do you pack them? So they are all like rectangles, okay, something like a few thousand rectangles. Now you have to place them all in such a way that they fit in nicely within the geometry of your chip, okay, and then you have to route them because those will be interconnected with each other. So you have to pull wires between them. If you don't place them right in a correct way, then routing will be a nightmare, because you will have some wires route from here to here, and then that's going to go over all of the other blocks and things like that, right? And routing is also problematic because if you have long wires, then they tend to have parasitic capacitances. If you put two wires very close to each other, they will again form capacitances between them, right? And what is the effect of capacitances? They will add to the delay, because every time you use that line, that capacitor will have to be charged up, right? So that's going to add to the delay of the propagation delay of the lines. So we have to keep all this in mind, and therefore there are a lot of very interesting algorithms which tell you how to do this placement and routing. And then you have the post layout simulation, which for digital designs is very expensive because of the sheer size of the design. And then you assemble these components into the full chip. You do a full chip design rule check. Design rule check means that you check whether all these transistor geometries are correct, whether the distances between the wires is correct, and things like that. Then you do a full chip simulation, again very expensive, and rarely you are able to do it adequately, and then go for tape out. In the analog, the design entry takes place in using a schematic editor. You draw the circuit using that editor. Then you can do a SPICE simulation at that level, and then have a custom layout. Okay, so you first do this layout, then you do the design rule check, then extract out the netlist, and then simulate the next netlist post layout. This is a slightly different way of doing things as opposed to the digital design. But then the circuits that we are talking about here are not as large as this, because analog circuits are very specialized circuits, difficult to design but not large. They contain only a handful of transistors, 40-50 transistors maybe. Okay. Right. Now I will not go into this course agenda right now, because you will be given a printout of the timetable of the courses. So you will be taught initially some of the concepts of how this chip design takes place in a generic sense, and then after the first week, I believe that you are going to first or 2 weeks you will split up into two different tracks for digital and analog designs respectively. And I believe computer science people would be more interested in the digital and CAD tracks, whereas maybe electronics people might, or electrical people may be more interested in the analog design part. Okay, that will be the scheme of things for the next few weeks. I hope that you have a nice time and you enjoy the course. Okay, thank you.